Hello. Firstly, I'd like to thank you for the invitation to speak here today. I won't be speaking on network methods, which I spend most of my time working on, but actually speaking on a problem that I've been working on since about a decade ago, based on conversations with Michael Rendell. We were interested in solving demographic problems by combining information from multiple sources. In particular, thinking about cases where we had multiple surveys over the same population of interest, but also cases where we had other information, non-survey data, registry data, or other population level information that we'd like to bring to bear. And the issue we had was that most methods that we used here either chose one survey to work with, or chose only the population level information to work with, because of the technical statistical difficulties of using all forms of information at the same time. And so Michael and I started working on means of trying to combine those, and in essence the work that I'm presenting today is an abstracted version of that's been developed over the last years. We've also worked very close with Sanjay Chaudhary from National University of Singapore over recent years, and most of the very good ideas, I think Michael and I would agree, are due to Sanjay here. All right, so the introduction, I've already given some comments along these actual lines, but the primary idea coming from demographic research is how to do regression analysis on survey data, one or more surveys, when we have population level information as well. So the classic idea, as we all know, is the surveys tend to have quite detailed information on a small number of individuals, while the population level information is very exact, tells us something exactly about the population we're interested in, but has very little covariate information or detailed information about the individuals. So the idea was to try to combine these two sources with complementary strengths and hopefully get the best out of both. All right, so I'll be looking at ways of doing this with three sort of goals in mind. The first I've already mentioned, bring in population level information. Very importantly is how to include sample weights. And this work, as it's developed, has a lot to say about the primary question which we all face, is when to include sample weights and when not to include sample weights in the analysis, so that the methods apply directly to that case. And the last one, which is we would like to reduce the impact of strong parametric assumptions about the underlying processes involved, and try to be as non-parametric as possible, or more to the point, be as non-parametric as appropriate at every point. Now, the methods are actually very general. They apply to most models to the most of interest. But I'll try to stick with the generalized linear model framework, or just basically regression. All of my examples will be regression because the vast majority of applications are along those lines. So I'm happy to answer questions about more general models if they arise. All right, so I'll start off with a very simple example. Some of the examples to start with are quite stylized, just to make sure we're on the same page and we know what's going on. So here's an example when we want to bring in population level information. It's from the British Household Panel survey, and we have a relatively simple case where the outcome variable is an indicator of births from time t to t-1 to t. So we're just looking at births, and the only covariate we have here is an indicator of the existence of at least one child at that time. So if across from survey data, so we have a cross tab here of those counts. In addition, we have simple information about the general fertility rate. We know the general fertility rate over the period which the survey is actually taken. So we have the survey information, we have population level information, and the basic idea is how to combine these two. Well, here's a simple way to actually do it. we'll consider, again, the stylized way, a simple logistic regression model for the birth probability here. We'll write that down here. And then all we're really doing is recognizing that the parameters in this model, the beta parameters, and the corresponding probabilities pi that they determine are constrained by the general fertility rate in this way, that the general fertility rate is P0 by pi plus P1 by 1 minus pi, where P is up here, the model for the birth probability. So we know that the parameters of interest must satisfy this deterministic constraint based on the population. So we could just fit this logistic regression model ignoring this, but the natural thing to do, viewed in this way, is just to fit the logistic regression model subject to the constraint on the equation. Implicitly, we can write down the log likelihood for this logistic regression model here and add it, maximize this subject to the nonlinear equality constraint implicit on the beta parameters here given by this form. So this is relatively straightforward to do. We can just use a nonlinear optimization problem subject to an equality constraint, a very well studied problem to solve this, and then we can show that it actually works. So once I could go into the details of this, which was spelled out in this paper. I won't say so much about it. The direct constraining approach, you can do it with SAS, say with PROC, NLP, or MATLAB, or R. And we show in these papers and related work that the estimator we get retains some of the nice, or all of the nice properties of the standard maximum likelihood in this case, asymptotically efficient, unbiased. We also derive equations for the standard errors involved and show that under correct specification of the model that the standard errors are reduced in this case because of the constraint. It's a very natural idea. We're adding additional information that should reduce the variance, and we can show mathematically it does, and it's actually nice you can prove that it actually does. And more to the point, as an aside, you could ask the what if question. Suppose we had a population level information on a quantity of interest. You can play that forward to see what the impact on the standard errors of your parameters would be. And so then you can make an informed decision on whether it's worthwhile going out and getting that. So if you find your standard errors are reduced by half by adding in a certain quantity that would take you only a few hours to get, then it's what we're doing, and vice versa. It's also important to state here, though I haven't said it very much, that if there is bias in the survey results, that the survey itself is off just due to incorrect weights or due to other issues with the survey, and under the assumption that the population level information is actually correct, what this method will do by the constraint will ensure that the parameters are consistent with the true values and hence do bias reduction also. So it will reduce bias, or at least the bias that is identifiable based on the constraint. So in addition to variance reduction, you'll also get bias reduction in this way. And I'm not going to go through this here. It's in the earlier paper, the 2005 paper, but we have software to do this, and I'm happy to expand on this various thing, but I wanted to move on to the newer work. Now, one of the difficulties with this is the optimization is hard to program and to solve. Or actually, more accurately, it's reasonably easy to solve if you're relatively good with constrained optimization routines. But to specify the problem, you pretty much have to specify each problem within that, program it directly in that, which can be hard. Hard, that is time consuming, but that's just worthwhile noting here. All right, so what I want to do is describe this new approach, and it's actually sort of a new approach also to do the analysis of survey data. So it's, in essence, when Mike and I sat down to think about how to do more progress on this problem, we decided we had to think a little more abstractly, and I think that led to a different way of thinking about survey design in general. So the basic idea, which I'll follow through here, is we think about the underlying surveys in this three-pronged way. So we think about an underlying population for which the finite population of interest in purple here is actually drawn. So the idea is we conceptualize the population of interest, finite population, as being a random draw from a superpopulation model, and indeed we draw n elements, n individuals from the superpopulation, IID from this, and they form the finite population of interest. Now once we have that fixed, we then draw the sample from the finite population of interest, and I've drawn a sample size n according to some sampling design D. That's just where it could be stratified sampling or some other form like that, or simple random sampling, but we have some design mechanism D. Now keep in mind, we're going to assume throughout, this is a major theme, that this D is either unknown or very complex. Now for simple random sampling or a stratified design with known stratification weights, that's fine, but we're also considering much more general cases than that. And if you want to have something in mind of what would be more general, well, suppose we have missing data, where the mechanism for the loss of data isn't known. And that's one primary case of interest here. Others are social network designs, but I'll get to that later. Okay, so the basic idea is we draw a sample of size n, and this is the sample drawn here. So note this is slightly different than the usual setup for survey sampling. We believe this conceptual framework has a lot of advantages to it. So in addition to that of the individuals drawn from here to here to here, we have variables involved. And we'll have a, this is somewhat stylized, but it's spelled out very specifically in the paper for the technical details. We have an outcome variable y, we have some covariates x, and we have some design variables d. Now the design variables are what determines this here. They're the factors that determine who is actually selected in the actual sample. So in particular, keep in mind the missing data interpretation of this, what determines who is observed or not, or who is missing or not in this actual process here. Unfortunately, you can't really see that in this here. This is y, x, and also variables d. Now, when we get down to the actual sample from the finite population of interest, to make this realistic, we assume we don't observe or necessarily observe all of the design variables. We only observe a subset of them. So we might not know all of the variables that determine who's observed or not, e.g. who's in the missing data or not. You might have this subset. So this is, you know, outcome, covariates, and who's involved. Question?
Question of clarification. Why is it looks like the design is some kind of function of the superpopulation, a part of the superpopulation?
Yes.
And that's not necessarily the same design from going from the finite population to the sample? Or?
Oh, that's very true, in the sense that we assume that the finite population is an IID draw from the superpopulation, so that the design, if you will, is known, and it's in fact a simple random sampling in some sense. And this design here is purely the linkage between these two. In other words, there's no relationship between this process and this process here.
So it could be like D1 and D2.
Yep. So you could have D1 and D2 here, and you could, but we don't actually do that. Yeah. Okay, so let me now talk about model specification, and some of this is technical, but it's also quite useful, so I'll go through it. So the first question is, as we'll keep in mind, we want to look at the relationship between the response y and some explanatory variables x. So one way to do the way we follow through is to use a classical estimating equations approach, which you're probably familiar with, but I'll spell it out because I think it helps with the notation in the very least. So we assume that we have some unknown parameter of interest, which relates y and x, and that we specify the underlying model, e.g. a regression model, through a set of estimating equations here. That is the expectation under the underlying population distribution f0 of some function psi of y and x, and the parameter equals 0. So we have these set of typically multivariate estimating equations. We assume psi is known, theta is not known. So that just to make it explicit, the simplest example of this and the one that we would often use is, say, for generalized linear models, logistic regression models. We'll actually use for psi here the corresponding score functions for the parametric likelihood. So this is basically just writing down the score functions of the likelihood. So satisfying these constraints would be satisfying a score function, which would be maximizing the likelihood. So it's basically the model specification is through this somewhat implicit mechanism, or is specified through this implicit mechanism, but it's basically as we typically do it. So we note we have this form here, and we refer to this as just a parametric constraint in the problem. Now, to specify the population level information, we do it pretty much as I did in the example of for Tiddly, but again in an abstracted way. There are some functions g which are of all of the variables we actually have, and the expectation of those functions, these are all random variables of course, of g is equal to some known parameter here. So the basic idea is the expectation of this is equal to gamma. So in my example, this was the general for Tiddly rate, and the functions here were functions the underlying birth events. So basically this is how we'll specify population level information. This is not actually too particular here, because note we have the choice of g. We choose g, so g can be quite general, and most population level constraints, well, almost all I can think of, could be specified in this way by appropriate choices of g. Okay, so we have the population level information in this way. Now the next thing is sort of more general, is to how to think about the design process. Now, this is somewhat more general than the setup we have, but that the setup required to solve this problem, but it's extremely interesting, so I will go through it. So the core idea here is that the distribution of the variables in the sample will typically differ from that in the population of interest. So basically, unless it's a simple random sample design, there will be structural differences between the distribution of the variables in the sample and the population of interest. And this is a very natural thing. So let S be the sample drawn from the population, and IS be an indicator of that. And then the idea here is pi S is defined to be the probability under the finite population of the sample being actually drawn, given the design variables. That is, the design variables in the population of interest. So basically, this is just a standard inclusion probabilities, which are used in survey design. But note, this is subtly different here due to the superpopulation model. In particular, or one thing that's important is these could be joint inclusion probabilities. They don't need to be the first order inclusion probabilities, i.e. the probability of each unit. They could be second order, the probability of each pairs of units, or higher order. This is just basically S being over all sets. I won't go into the details here, but basically the easiest way to think about this as just the first order inclusion probabilities, and I'll talk about the more general case if there's of interest. Okay, so we then make a couple of assumptions, non-trivial but interesting from a methodological standpoint, about the relationship. Because the key thing here is how we're going to make progress on this design, which we might not necessarily know. How can we get some traction on it? We make the assumption that the pi S are conditionally independent of the outcome variable and the covariates in the population of interest, given the design variables here. Now let me just take a step back. There's a key difference here, a key fact here, which is important to grasp. Within this setup, the pi's are random variables. And so this is, in some sense, fundamentally different than the way we normally think about sampling designs. We think about the pi's as inclusion probabilities as being fixed known constants. Now, the random variables, because they depend upon D. D being the design variables, and the design variables are randomly drawn from the superpopulation. So this makes the pi's random variables, so this statement makes sense, i.e. they're random variables rather than fixed constants. So in particular, we assume this for all possible samples drawn from the population of interest. And with a little bit of algebra, you can show this is equivalent to the statement that the inclusion probabilities are functions of the sample and the design variables alone, i.e. they're not functions of x and y. So we have this quantity. So it gives us determinism of the design probabilities of the inclusion probabilities as functions of the design variables. Right. We make another assumption here, which I won't dwell on, but it's important, is that the inclusion indicators are conditionally independent of all of these variables given pi s. Right. So what this actually means, implication of this, is a conditional expectation of the inclusion in the sample given these are just equal to the value themselves, and we have the conditional independence of inclusion in the sample and the design variables given pi s. So what does this actually mean? Well, the basic idea is that inclusion probabilities pi s contain all the information about the sampling mechanism. Now, assumptions we've made are actually weaker than this, but you could probably scrub what I've said mathematically in the previous 2 pages and get down to this. We say knowing the inclusion probabilities gives us all information that we need to have about the underlying design. Right? So there's mathematical backing to this, why this makes sense, but it's incredibly helpful from a methodological standpoint. Now, I'll give you some examples of this. Suppose we have multiple surveys. If you have multiple surveys with different weights in them, it's very difficult to think about conceptually how to include include joint weights in the multiple surveys, especially if details of the sampling design that generated those weights are not available to us. What this assumption basically says is that it's sufficient to have those sampling weights to actually do the analysis on multiple surveys. All right, so now I'll get into the methods involved. Question? Yeah.
About the kinds of designs that are allowed under the assumptions that you specified.
Yep.
You're thinking of, is it the case that you're thinking generally of multiple sort of well-behaved sort of probability designs that could be different from each other, or are you interested in like the kinds of problems that we have if telephone surveys are breaking down and the design is unknown?
Both. If we know the designs, this definitely applies. And if we don't know the designs, we're assuming that we can work out all the information necessary for inference based on the weights. So if it's telephone surveys breaking down, we might not know the actual mechanism for how they're breaking down, but the weights that we actually have will enable us to infer enough of the characteristics of the actual mechanism to do inference for the relationship between y and x. Cross K, yep. No. Pi observed? No. I'll get to that in a minute. It's obvious, not an obvious, but a very natural question about, okay, well, how are we going to get traction on this? So we're going to get traction on it using a likelihood approach, because I think likelihood approaches, by placing you in a sort of valid statistical framework for inference, make it possible to make progress without getting lost in ad hoc aspects of it. So we'll let fi of s be the conditional distribution of the variable v. I'll just use v to represent all of the variables to keep a shorthand notation, given the I is in the sample. This is the key thing. So this is a conditional distribution in the sample of the variables of interest. So we then just use Bayes' theorem. It's sort of a simple use of Bayes' theorem to show that the density in the sample is related to the density in the population of interest, F naught, which is unknown, through this relationship here. Simple application of Bayes' theorem, whereby the way we'll define these is that these guys here knew so-called the conditional inclusion probabilities, the expectation of the pi's given v, the variables of interest here, which we refer to as the conditional visibility. We use the term visibility because it basically says how visible are certain variable combinations in our sample. How often do they appear in that way? And the denominator here is, writing this out, it's basically just the unconditional probability of pi in the population of interest. Or we can view it like this, as the expectation over the population of interest of the v's. So this is just for normalizing purposes, but we see the relationship. So these guys are the unconditional, and these are the conditional versions. So refer to these as the overall visibility factors of the element in the population of interest. Look at these two quantities here. So this gives us basically a relationship between what we observe in the sample versus what we're interested in and what is the population form of interest. So what we choose then to do is to model the population distribution unknown with some parameter theta. I'll come back to this. And model the conditional visibility with some parameter alpha. So we need to work out models for these in terms of methodological issues. And I'll come back to the example, which I'm going to give a serious example on fertility at the end, where I'll talk explicitly about these models. But at an abstracted level, we need to represent models of these two if we're going to write down a likelihood. So we do write down a likelihood. It's a composite likelihood. So as all likelihoods are, it's a probability of what we actually observe. So we observe the frequencies of these within the sample. So we write down the probability over the sample of the product here. It involves the variables v and alpha and theta. It's a composite likelihood. And so then what we could do is maximize this composite likelihood over alpha and theta to get the parameter estimates and then work our way back up to get to the model parameters themselves by maximizing this quantity here. Now let's think about one. We need to have a model for the population distribution of these variables. That's in a finite population. Of course we don't know it. So that people often write down parametric family models for this, and that's a natural way to do it. And in fact, that's what Michael and I did in 2002-2005. What I want to discuss here is a different idea, which is to use empirical likelihood, i.e. non-parametric representation of the population distribution. So explicitly, we'll follow an empirical likelihood approach here. Now, I've got a few slides on reviewing empirical likelihood, just in case you haven't seen it in a while. I'll say a little bit about it. I'll go through them relatively quickly just to get the idea, but I'm happy to come back and spend more time if there are more questions on it. It's an extremely interesting idea. But I'll just say what it is in one sentence or so to help. So basically the idea is what we want to do is use the framework that we use for likelihood estimation, maximum likelihood estimation for parametric models, but slowly ease off the parametric requirement to move as far away from the parametric requirement as we can. This can make it less parametric. Now what by less parametric is have it have more parameters in some sense, so not be a smaller parameter form, but have less and less tie to the parameters of interest. So can we push the likelihood framework to its natural limit, if you will? And empirical likelihood, in some sense, can be thought about pushing the parametric likelihood approaches to the natural limit. So it's due to very clever work by Art Owen, and I'll briefly just go through it here. So suppose this is an abstracted one, and I'll come back to the specifics in our case. Suppose we have an IID sample for some distribution F0, and we want to do inference about F0 based on just an IID sample here. And we know where F0 comes from some parametric family here. So Owen says, suppose F is a member of this, then the non-parametric likelihood for F, defined this is a parameter of interest in a general sense, is just the probability of what we observe given the variables D, which is just the product of F of Zi minus F of Zi minus. This is just the atom, if you will, that focuses on Zi, because this is a distribution function rather than a density function. What reason it looks a little odd here is we're trying to deal with continuous distributions and discrete distributions. But this is just the direct likelihood of it. And its likelihood in this sense, that L is the probability of the sample from F. All right. So a natural thing to do is say, well, let's estimate this just by maximizing this likelihood. But then we shake our heads and say this can't work, because if F's a continuous distribution, then the likelihood is uniformly defined to be 0, because you just take that limit and you're done. So that's not going to work very well. Now, what we can do, though, is think about a slightly different form. If what we then can actually do, this is F is discrete. We can put positive mass in every sample. So in this idea here, we can identify F only through the corresponding weight. So let Wi be this difference here that is assigned to each sample point, and write down the likelihood in this way is just a product of these weights. And then what we can do is use, we can think about the optimizing these weights subject to the natural constraints because they're probably masses that they're non-negative and they sum to a 1. So this is a member of this simplex here. And so we can then show, Owen shows that the non-parametric likelihood is maximized when the weights are just 1 on n. And we get what we would naturally expect, that the natural estimate parametrically is actually the empirical distribution function over these actual forms. So he shows that this is actually true, i.e. we get the natural result out of this. So what happens when we want to apply that result with auxiliary information? Well, we can use exactly the same trick. We can use the non-parametric likelihood, but constrain the parameters with the population level information to get a constrained non-parametric or constrained empirical likelihood. So use empirical likelihood in place of the parametric likelihood, but everything else stays the actual same. So in our approach, we can write down our natural empirical composite likelihood in this way, in the same form as we've had before, and incorporate the population level constraints. So I'm skipping over about 20 pages of mathematics, but basically what we can show that this actually works, and you can show that the maximum, when you maximize this composite likelihood, it's strongly consistent, asymptotically unbiased, and Gaussian, in a sense that I could spend a lot of time talking about, but I'll spare you right now. So basically what we're going to do is use this maximum empirical likelihood approach in place of the parametric approach. All right, so I'll just come back briefly to the British Household Panel Survey before I get to the application. Just wanted to write these down to show you they're real. Of course, you don't study them too much. We can write down actual core constraints for the logistic regression in this form here as just these mathematical equations. We have the population level constraint, which you can write in this form, which is the sum of this difference. Again, just to be specific, there's simple functions. The function g is here of these constraints just by taking this difference here. And we can then run this through the process here and maximize these. And just to give you, again, these are actual results, but just to get a sense of what's actually going on. So we have estimates in the model parameter beta naught, what we get under the constrained, i.e. with the population level information, and the unconstrained, and we get estimates of the birth probabilities here. So all this, and these are standard errors involved. So the basic idea is that when you add the constrained information, you actually get dramatic shifts in the level of these parameters, and we get variance reduction also. But in this case, what we get is a substantial change in level, i.e. we get bias reduction is a major choice here. All right. So I could go through a little bit on that, and there's some notes on it, but I don't really want to dwell on it. The basic point here is for this sort of toy example, the process actually works in a very natural way. The only other comment on that page is sort of an interesting one, which is that if you the constraints typically, because of the nature of them, will only give you a lot of information about a subset of the parameters of interest. So what you see is for some parameters you get bias reduction and variance reduction, and for other parameters you get nothing. Don't get bias reduction, you don't get variance reduction. And the idea of this is, of course, the parametric constraints, the population level constraints will tell us nothing, might not tell us anything about certain subsets of the parameters of interest, and as such are not very helpful at all. So that's just a general feature of it, and I could say more about that. So we actually have a relatively sophisticated two-step maximization method that's numerically stable and computationally stable, but it won't really focus on that here. We do show in practice, and it's an empirical statement, that the parametric constrained method and empirical likelihood method tend to give very similar results. Now, they're not going to give similar results when the parametric model, if the parametric model is correctly specified relative to the non-parametric model, you lose some efficiency by using the non-parametric form, but it will basically do reasonably well. Now, the interesting case is when you have misspecification of the parametric model, and so your parametric inference will tend to be biased relative to the non-parametric form. But this is a classic bias-variance trade-off. In our experience, the variance reduction is greater than the bias, so you're typically better off using the empirical likelihood form. But that is an empirical statement rather than a theorem. Okay, so now just talk about a particular case, and this is sort of help cement ideas about a talk which is largely technical. I'll look at an example of fertility in the PSID, look at first birth probability. Well, first, as everyone in this room knows, or most people in this room know, first attain a peak at age 20 and then a much higher peak at age 28. So here's a classic plot just to orient ourselves. We have age down here on this form, we have ages, and over here we have the first birth probability here. And we have a number of different things plotted on it, so I'll go through them. Now this is population numbers on these first birth probabilities given here, and they have this classic two-dip process here. They're very smooth because they're based on population level information. And this is what you get from the PSID unconstrained. You get, if you compute them directly from the PSID, and they're bouncing all over the place. And reasons for this, well, the PSID is a sample. It's got sample variability involved, relatively complex design with clustering, other things like that. So there could be issues with the PSID in terms of, well, many issues with the PSID as we know, but the basic thing we're seeing here is sampling variability. So in a nutshell, what we're trying to do here is say, well, look, if we know that these parameters or these characteristics in the population follow this smooth curve, and this is what the PSID is giving us, shouldn't we be able to constrain estimates based on the PSID to be perfectly consistent with this curve? And that's exactly what these methods do, in a nutshell. Question? No. Yeah.
I think I'm following it, but I'm not certain. If I think about this from a Bayesian standpoint, and we have this extra information, this population level information, do we not just establish a prior for that population information and put it in the model and obtain the same thing?
That's exactly what we've done. Now, but keep in mind, in this case, your prior says the probabilities are exactly this, with probability 1. I know for sure they're these numbers. Now, if that's your prior, that with probability 1 on these points, then our method is exactly a Bayesian method with that prior. Because what will happen when you play through the Bayesian method, when you play through the math, it'll lead exactly to this likelihood. Because what the prior will do is constrain the parameter values to be exactly on that curve. Because that's what you know. With probability 1, they're on that curve, and it's exactly what we get. Now, interesting steps that... Oh, okay. Right. So the next step would be to step back and say the prior is not a point, i.e. exact population level constraints, but these are known with error, perhaps due to some bias in the actual population level information or registry information here. So you could put a distribution over these, or a joint distribution over this curve. And that would be your prior and have uncertainty. So in a paper that Michael Rendell and I published in Demography maybe 2 years ago now, we actually do exactly that. Bayesian fertility estimates based on things. So it's a very, I think, a very interesting idea and a very useful generalization of this approach.
So what's the advantage of doing it in a, I think that this, one of the reasons I like the Bayesian approaches is just, frankly, it's easier to get the standard errors, essentially, with the byproduct with estimation process. So here you've got, I was doing a lot of tedious math to derive the standard errors. What's the advantage of a maximum likelihood as opposed to a Bayesian approach?
Yeah, there's a lot of questions there I could back out of, but the short answer is there's a lot of tedious math, but it's done once, and I've actually done it. So you plug it in your computer, you hit go, and it gives you the answer. It's the short answer now. It's actually not very difficult to do. In fact, we have the formulas in the paper. So they're actually done. The advantage of maximum likelihood in general is that if you have this population of information directly from different information source, you don't need to specify the prior. That's one. And secondarily, in empirical likelihood view, you don't have to specify the, in a classical Bayesian approach, you need to specify every aspect of the model through a distribution or a form, a parametric form. We don't need to do this here because it's a non-parametric representation of it. So they're the two advantages of it. Having said that, we do have a likelihood approach here, and it's very natural to add priors to the parameters of interest in this context. There's nothing wrong with that. And so, in fact, Sanjay has taken this approach and placed the empirical likelihood within a Bayesian context and written a paper on it. So it's an extremely good idea. But I guess the major point I want to make is these two things are not incompatible with each other. We've used maximum likelihood here. We've maximised the empirical likelihood, but we shouldn't step away from the fact that what we've done is written down an empirical likelihood, so hence we could have a Bayesian empirical likelihood approach, and you could have the pooled information from the priors, which will give you a lot of information as well. So very good questions. Okay. Okay, so just to work through this, we have Y as an indicator of birth. We let YI, there'll be some notation here, but I won't, just to make it specific. We have IJ just be indicator of age, IM to be indicator of marriage, and MD be marriage duration in this thing. For the PSID, it's sort of interesting because we do have a lot of structure in the PSID, but in particular I'll just focus on two different subsamples here, the SEO, which tend to be lower socioeconomic status subsample, and the SRC, the standard one. And what we've done here is plotted the actual PSID weights, which we've actually observed in this case, or observe in the sample. So the weights here for the SEO sample are way down here because their probability of inclusion are much higher. They're oversampled folks. So their weights are way down here, and you can see there's a tail here, but compared to the other guys, their weights are very low in this area. So we basically definitely want to take this into account. So these are the weights that we're basically, in a nutshell, we're saying these weights, we could just use them for direct weighting and use standard design-based estimates in our process, or have regression ignoring the actual weights. But the core idea we're trying to bring across here is these weights contain very interesting information about the underlying design themselves. We should be able to exploit the weights to improve the overall quality of our estimates if we just knew how. What this approach gives us a way to answer the how question, how to incorporate the weights in an appropriate fashion. So these are the weights we'll be working with. Just a little more notation. I'm going to just do logistic regression. It's sort of a generalization for this illustration. Here on the covariates of interest, and I've just written down in gory form a logistic regression form, where the basic idea is we have underlying indicators for age. We're picking up the non-parametric age effects here, although you could include many more demographically relevant variables in this model. And I've written down again these guys just to be explicit, just to show you how they work, though. We write down an overall mean for the logistic regression. The unconstrained likelihood is just a logistic regression. We can write down the score for the logistic regression, and we can write down, so this is written here, and we can also have constraints from the population level information. I've just written them down. I don't need to memorize them, but it's just a point. Although it's somewhat laborious to write down, it's relatively straightforward. So what actually happens, we then run this empirical likelihood procedure with the population level constraints, and this is what we actually get for the estimates. So what I've done here, just because there's so many different parameters involved, is plot the parameter estimate down here. These are the age values here, and these are the other covariates involved, and these are the actual values. So just a plot to get the sense of what's actually going on. So we have the unconstrained, which are these guys here, following the line. Our estimate, which is the CE, and CS, which is a so-called Chen-Sitter, which I could say more about, which is a competing estimator from the 1990s. And what we can see is are the parameter estimates in terms of overall level change. So you can see the Chen-Sitters down here, which is relatively close to ours. The unconstrained ones, as you see, especially for these upper ages here, which were bouncing around, if you remember from the original plot, they're substantially higher. So it's about 1 or something on a log odd scale. You've moved those guys around. Where our estimate and the Chen-Sitter are reasonably close. So in terms of the overall level, you can see the impact here. And if you look at the variances, which you compute by our very tedious computations, well, actually the computer did it for us. What we have here is the overall variance estimates. The unconstrained here, the variance estimates are about 0.8. The Chen-Sitter about 0.6, and ours are about 20% better for the empirical likelihood here for these actual forms. Now, if you go back to look at what the implications are for the age effects here, they'll exactly match what the parameters were in the original plot. I haven't given those because they're exactly right by the constraining form. All right, so that's in terms of the actual form. This is, again, a somewhat stylized example, But the core point is you can apply this method in pretty much the same way as you normally do by bringing in either population level information or weights, and what we'll see is an improvement in the process. One thing I haven't shown here, and I could have, is a model for the actual underlying weights. Now the weights themselves, we modeled the log of the weights directly as a gamma regression function of the same variables we had in the outcome. Now basically through that process we in essence draw the information from the weights and include it in the empirical likelihood. And it's that gives us the difference between that and the Chen-Sitter approach, the direct modelling of the actual weights. So you can get something like an order of a 20% improvement by actually writing down this model within this approach, i.e. treating the weights as random variables or treating the weights as random. All right, so a little bit of discussion here to end. Empirical likelihood is extremely useful, especially for survey data and a lot of demographic survey data. Because even though it's a somewhat abstracted theoretical approach, it has direct applicability in this case. It gives us a way of doing what we typically think about as post-stratification of surveys, especially on a lot of easy way to do post-stratification, being more complex post-stratification ideas. This is just a comment here in terms of the question. The incorporation of prior information can be easily done, and just we haven't spelled it out here for various forms. So what have we done in this work, just to come back and hit some of the major points? Incorporating survey weights into empirical likelihood, which is very hard to actually think about the way that does. So we have a framework for doing that. And the empirical likelihood can be talked about as a non-parametric likelihood under the true population distribution. We've done that in this way. We've assumed explicitly that sampling weights contain all the information about the design, and that gives us a way to link the sampling distribution to the population distribution of interest, and so you can have sample weights, population level information, and inference within this form. So I've got two other comments to make, which I'll now make. One is the reason we sort of work so hard on this is to use it in a more complex designs, in particular link tracing designs, things like responder-driven sampling designs. And in those cases, because of link tracing, your sample is very dependent upon each other. Who you observe later on in your link tracing design depends upon who you observe earlier on. So your second and higher order inclusion probabilities are very, very informative about the actual process. So instead of using first order weights, which is what's usually done, we use second order weights and third order weights to improve the efficiency. And we find this leads to dramatic improvement in network sampling design inference. I haven't described that here. The second thing, and I found this really interesting as a statistician, was that if we take away the population level information and just ask ourselves, what would we do for standard survey designs? What does the empirical likelihood estimator we have look like compared to standard designs? And the short answer is if you deal with the simplest possible case, it returns the Horvitz-Thompson estimator. That the maximum likelihood estimator, empirical likelihood, is actually the Horvitz-Thompson estimator, i.e. the standard design-based estimate. This gives a framework to think about how standard survey design, the one we've been using, the workhorse for the last 50 years, that's actually a pretty good thing to do because we've given a likelihood framework in which it's actually the maximum likelihood answer, which I found really interesting. The second thing, and even more interesting, is we constantly bang our heads against the question of how to deal with sampling weights in surveys. When to include them, when to not. When to use them in regression, when to not. We know we should include them somehow, but we don't know how. Well, within this framework, it now makes sense to do that. And the short answer is what you should do is model the sampling weights based on variables in the survey. Use that model to estimate the expected sampling weights, the conditional expectation of the sampling weights given the variables involved, and replace the sampling weights in your standard estimators with those conditional expectations. And that will give you the appropriate weighting form. That's a sort of a rough answer to the question, but that sort of makes sense. Because what it's basically saying is weights have error in them, and what we should do is get rid of that error by looking at conditional expectations, i.e. smooth the actual weights. Use smooth weights and you'll tend to get better inference when you use smooth weights. So I think I've got a lot more to say, but I'll stop at this point and I'm happy to answer any questions upon any of the issues that I've touched upon. Thank you.